Welcome back, everybody. We're gonna restart up what we were working with. And I didn't expect us to be able to just move straight on from this problem from Tuesday. I wanted to talk about it again, just to kind of reiterate what's going on. So the actual formal definition is a lot more convoluted than you think it would be. And so I made a mistake here. This is actually not f of g prime. This is not the derivative of f of g of x. That's not true. In order for it to be the derivative of f of g of x, it would have to be f prime g of x times g prime of x. I misspoke. I was trying to find another way to make it relatable, but I misspoke. So, in its formal language, it's very, very difficult to understand. It's best understood through practice. So what you look at this and you say, well, I can't really do any integration on it, so I will do what we call a u substitution. So you make u equal to x squared plus 1. And then there's this little bit of hand-wavy math. So you take the derivative of u with respect to x, and you get du dx is equal to, in this case, 2x. So all derivative rules still apply. Chain rule, product rule, quotient rule, all those things are still at large. And then what you do in quotation marks is you multiply both sides by dx. You can't actually do this. Can't actually do this in real life. But much like the rest of Europe at the time, it made it more intuitive. So they were able to actually figure out these integrals faster. So if you are able to think of it like a fraction, then you could rewrite it as du is equal to 2x dx. And then what we do is we solve for dx. And the reason why we're doing that is that then we can take this dx and replace it in the formula. So we can change dx to 1 over 2x du. There is another way to do this that some teachers do. They do a thing called term matching. There might be another name for it, but basically realizing that du is equal to 2x dx, when you have that integral of 10x times, and we're going to write it as u to the 4th dx, you could rewrite this as 5u to the 4th times 2x dx. So they try and term match it so that this is du immediately. So like what they do is they skip this solving portion and just take this and replace it here. That's term matching, and it's great. It's perfect. It's fine if everything is nice and neat. Like if it already is 2x times x squared plus 1 to the 4th, not too terrible. If it is 10x, not too terrible. But what if the integral was something like this? What if instead of being 10x, what if it was integral of pi x times x squared plus 1 to the 4th power dx? There's not really a way to get a pi, or like get a 2x out of pi x. You have to do something really, really annoying. You have to do this. You have to do pi over 2 times 2x. And it works. It's totally fine, but it's just something that I find to be a little bit tedious. So what I do instead is the method of just solving for dx. And so that's what I've done here. So I've divided both sides by 2x. And as a reminder, the reason why I've written it this way is that the du, whatever the differential is, so dx, du, dt is kind of like the period at the end of the sentence, and you don't put the letters on top of the or underneath the period. Period goes at the very, very end. That would be my argument for why it shouldn't happen. That being said, plenty of teachers and plenty of textbooks even will say, we'll have you write it like this. They'll write 10x u to the 4th times du over 2x. They'll do that. That's fine. I'm not going to mark you wrong for doing that. It's completely legitimate. It's just I'm one of the people who doesn't like to do that. I like to make sure it's kept separate. So after you've done that, then you can make a bunch of substitutions, hence the name integral substitution. You can substitute u in for what you claimed it to be. So x squared plus 1 is u, so this is now x squared plus 1 to the 4th, x squared plus 1 to the 4th is now u to the 4th. And then dx, as we've solved here, is 1 over 2x du. And as luck would have it, and this should always happen well, almost always should happen for you, that when you do this, all of the x terms or all of your original variables should go away, and you're left with the integral purely in terms of your new variable, u. And so when you do that, you can take this integral really quickly by the power rule. That's 5 times u to the 5th over 5, or just u to the 5th once things cancel. But our original integral was purely in terms of x, so we're going to rewrite it in terms of x. Just like and a reason why we do this, do you remember logarithmic differentiation? Remember when we had to do this, like when we had y equals x to the x, and then we'd apply natural log, and then at the very end, you get 1 over y times y prime, and then you'd multiply by y, but our original integral was purely, or our original function is purely in terms of x. So instead of writing y equals y, or sorry, y prime equals y times, I think it'll be x ln x plus 1. Instead of that, we wrote it as x to the x. Same idea here. You want to write it in the original variable in question. So you probably are wondering, well, how Phil, how did you know what to choose for your integral substitution? Well, the thing is, you just, as you go along, you have to learn what's right for you. Y-O-U and the letter U. That's not the joke, by the way, but the joke will happen today. How do you mean multiple rules?
Like, example, like you can use one rule to solve it this way, but I didn't solve it a different way.
There are several opportunities to do things differently. You can do, sometimes if you don't get it right on the first go, you can do an additional integral substitution. I had one for that. Though it turns out that if you can solve a problem with 2 integral substitutions, you can actually solve it in one, which we don't really go over, but I'll talk about in a second. There is another thing at the very, very end, which we won't get to, which is called reverse engineered U substitution. It's not actually the name of it. If you look up online, reverse engineered U substitution, you won't see anything. I'm trying to make it a thing, because no one really has a name for it, but it makes sense to me to be called reverse engineered U substitution. I should change that. That should be a lowercase u. But either way, so there are multiple ways to solve problems. But at the end of the day, it's what do you want? Come on, guys. That's hilarious. That's hilarious. Okay. But trust me that there will be a better joke soon. So the thing though is how do you figure it out? How do you figure out what's the best choice for you? And there's no one right answer. What you have to learn to develop is your own toolkit. Now, there are typical choices, but beyond this, as you continue on your mathematical career, integral substitution shows up time and time again. If you take Math 182, you'll talk about trigonometric substitution, which is a type of integral substitution, but it's a very niche type. And so that's a new way to try and do integral substitution. You'll also do partial fraction decomposition, which ends up requiring U substitution in it. Trigonometric substitution, not just integration by parts. All these things require U substitutions. And so you just have to learn to work with it and be comfortable messing around. Now, these are my 3 main choices. So typically, I will choose something inside a radical or a large power. So in this first example, the best choice would be U equals 2x squared minus 3x plus 5, which would mean that du would be 4x minus 3 dx. I'm not going to solve the problem. This is just free practice, but if you do this, you should get the right answer. Yes. Yeah. So, excellent question. Is it always that you make it U? No, actually. There's a problem later on that will actually, the original variable ends up being U, so we have to choose a different variable. So in that vein, typically, we always, if it's available, we'll choose U. But that doesn't mean you can't use a different variable. If you wanted to, you could just, instead of doing U substitutions, you could make this a puppy substitution. You could do that. You can make puppy equal to 2x squared minus 3x plus 5, and it would still work out. But the convention definitely is to use u. And most teachers will do that unless absolutely forced to do something different. With the second one, this is the integral of sine of y times cosine of y minus 3 to the pi. So a good option here would be to do cosine of y minus 3. That's the thing inside of a large or a weird power. So we'd make u equal to cosine of y minus 3. And that would mean that du would equal negative sine of y dy. And if you want to, try and solve this one and you will get the right, you will eventually get to the right answer. That is the first suggestion. If you ever see, the derivative of cosine is negative sine. Then something inside of a denominator, like typically the whole denominator, but sometimes in conjunction with option 1. So maybe a large power within the denominator. So for this first one, definitely the right choice is u equals 4b squared minus 2b plus 3. But for the second one, you could try to make it c to the third plus c to the fourth, all raised to the fifth, the entire denominator. And I believe it will work out in a very, very roundabout way. But that's not the easier option. The easier option would be to choose u equal to the inside of that large power in the denominator. U equals z cubed plus z to the fourth. And I forgot to write here, this would mean that du is equal to 8b minus 2, parentheses db. Because remember, the whole thing is being multiplied by, yes. Where am I getting the outside? So with these problems here, this is just showing you what you should choose for you. I'm not actually solving these problems. That's for later on. We're going to do several of them soon that like actually go through the whole process. Is that all right? So in this case, dz or du, excuse me, would be 3z squared plus 4z cubed times dz. And solving for that, I guarantee you will get the right answer. And then the last initial choice for a typical u substitution would be things inside of functions. So e to something, tangent of something, natural log of something, sine inverse of something, any of those types of things, those are good options. So in this case, you have 27 secant squared theta times e to the tangent theta. You could try and make, there is a quote unquote large power here with the secant squared. So you could try to make u equal to secant theta, but you'll find out that it doesn't work out. A better option would be to make u equal to the inside of the e. So u would equal tangent of theta. So that means that du will equal secant squared theta, d theta, and that'll work out. And this last one here, you see that there's kind of two choices based, like if you're looking at option 2, a good option for a u substitution would be to make it the denominator. It actually won't end up working out, but it's a good thing to try, but that won't work out. In fact, for this one, the better option is to make u equal to the third root of x, which is equal to x to the 1/3, which would mean that du is 1/3 x to the negative 2/3 dx. And typically speaking, if this happens, if you have to deal with a radical, it's best to convert it back to radical form. So, which equals 1 over the 3 times the third root of x squared dx. Yes, Ron. Sorry, say that one more time. Mm-hmm. Yes. So, great question. Because you don't know. you like, this is the thing, this is the thing that I love about mathematics. Honestly, this is why I love this section the most, is that unlike with differentiation, there's always a rule that you can do. You can always like, I can give you the nastiest function possible, and you'd still be able to take the derivative because it just obeys all the rules. With integration, that's not always the case. Sometimes you need to try things and they won't work out. That's not a reason to stop. That's a reason to say, that's not the way to go about it. Let's try something else. So you could try to do u equal to the third root of x squared in the denominator. And you try and do it. And I'm going to show you like that process in a second. And you'll see that it doesn't go anywhere. And so you have to go back to the drawing board and start again. So there will be plenty of scratch paper for this final exam. And for the I'm happy to give scratch paper on the next quiz. But the point being is that sometimes there is no right answer, like there is no one right way to go about it, and there's not a consensus of which is the best choice until you actually find it. But the key to success is that picture right there. A Maine Coon hanging on by a thread. Right? You got to hang in there. Don't give up. Just because you got it wrong doesn't mean you should give up. Like, I don't know who heard us and thought in mathematics you have to be right on the first go. It's not true. You rarely are right in mathematics on the first go, especially as you get further on in mathematics. It takes me, like for my courses when I was a grad student, it took me typically weeks, 2 weeks, 3 weeks to figure out a problem. I tried a million different times and never get it right until finally some stroke of genius happened and I figured it out. So it is not an excuse in my class to just give up because you did a first U substitution and it didn't work out. That isn't it. Like, that is a reason to try again. There's the whole thing. Like, I'm going to quote the great movie that is The National Treasure, that is the movie The National Treasure, and say that there's the whole story he tells about what's the guy who invented the light bulb? Thomas Edison. He had tried 1,000 times to create a light bulb, the incandescent light bulb. And when someone said, like, did it hurt to fail 1,000 times? He said, I didn't fail. I just learned 1,000 ways to not figure out, like, not create a light bulb. In the same way, you're not failing. You're just figuring out what doesn't work. I can tell you, I've taught Math 181 and 182 numerous times, and I've taken it. And I've taught my friends it when I was in college, and the ones that I knew that were going to succeed were the ones who weren't afraid to keep trying, to keep going at it, and not just keep trying, but try something new. Even if their original method didn't work, they would try something different, and they would get the right answer eventually. Tenacity is the key to success in college. Being willing to be wrong and be okay with being wrong, and then keep working forward. That is the key here. So please be like this Maine Coon kitty. He's looking determined. Like, let's add a little bit of, he's determined. So I made this like 3 years ago, and I still have it there. So he's a determined kitty, and so are you. So I'm going to do this several times during this lecture where we go a wrong route and see what happens. So I'll let you know when we do that. But anyways, the thing I want us to be comfortable with is just claiming a U. That is the other thing that I've experienced. Students' biggest hurdles is just starting the problem. So try a U substitution, even if it doesn't work. What's the worst thing that can happen? You have to erase it. I mean, on the exam, the worst thing that can happen is you get a 0 on it. That's a bad thing. But like on your whole, on practice problems and stuff, the worst thing that can happen is you erase it. That's not a big deal. So for this one, I'm going to let everyone get a chance to think about it. What do you think a good U substitution would be? Take a second, look at that problem, and what would you choose U to be? What do you think? G? The inside of the denominator, like not the whole denominator. And actually, let's go ahead and do that. Let's say you made U equal to the the square root of 2t plus 3 cubed, which is 2t plus 3 to the 3/2 power. This isn't going to work out. I mean, it might work out, actually, now that I think about it. in a very, very roundabout way, but we'll see. Then du would equal 3/2 times 2t plus 3 to the 1/2 times 2 by the chain rule times dt. So that's really 3 times the square root of 2t plus 3 dt. So solving for it, you get that dt is equal to 1/3 square root 2t plus 3 du. And if I were to try and finish that, I get 1/u times 1/3 square root 2t plus 3 du. And there's nothing for it to cancel. There's nothing for it to cancel, so this isn't probably going to work out. There's nothing that's going to get rid of that square root. So instead, what I'll do, and I'm going to write the process here, by the way. I'm going to write a step-by-step process. So step 1 is to choose u and differentiate with respect to x. Choose u and differentiate. Secretly multiply by quote unquote d variable. So dt in this case would be dy in the second problem. It'll be dx in most cases, but you're going to secretly multiply so you don't have to, all right, that's fine. So in this example, we're going to make u equal to 2t plus 3. And that would mean that du is equal to 2 dt. There's a hidden middle step here where it gets du dx is equal to 2, and then I multiply both sides by quote unquote, sorry, not du dx, du dt. Where I'm I'm technically multiplying by dt. That's that middle hidden step that I'm going to just skip. So initially, you take the derivative, you get du dt is equal to 2, but then you multiply by tt on both sides to get du is equal to 2 dt. Now, with that out of the way, step 2 is to solve for d blank in step 1. So in our example, we've got du equals 2 dt. You're going to divide both sides by 2 to get dt is equal to 1/2 du. And the last step, step 3, is to substitute both into the equation and integrate. So you're going to substitute both, like you're going to substitute your dt in for it, and you're going to substitute your u's in for it and get what you need. So I'll let you write that down, and then we're going to move on. We're going to actually start doing the problem. So you're going to choose the u, you're going to differentiate it, and then multiply by dt or dy or dx or dz or whatever it may be to get du is equal to 2 dt in this case. And then you're going to solve for the independent variable. So in this case, t. The next case, you're going to be solving for dy. In the case after that, you're going to be solving for dx, so on and so forth. And then you're going to substitute those things into the equation. So what we'll get is that this is equal to the integral of 1 over the square root of u cubed times 1/2 du. And from here, we need to integrate it. And it looks like it's not integrable at first, but remember about the properties of exponents, we're going to convert that radical into exponential form. So this is actually equal to the integral of 1/2 u to the negative 3 halves du. And we've done it in such a way that now there is an integral purely in terms of u. And so we can actually integrate this. So this will become 1/2 times u to the negative 3 halves plus 1 over negative 3 halves plus 1 plus a constant c. But remember, this is negative 1/2. This is negative 1/2. So the 1/2s cancel. But that negative sticks around. So we've got negative u to the negative 1/2 plus a constant c. But we want our original integral to be in the same variable in from the beginning. So we claimed that u was equal to 2t plus 3. So this will be negative quantity 2t plus 3 to the negative 1/2 plus that constant c. And if we were going to use this for anything, I might convert it back to radical form to write it as negative 1 over the square root of 2t plus 3. But since we're just finding this indefinite integral, we're done. Any questions on that? We're writing it down. This is definitely weird. It's just we're going to have to do practice with it. So if I can impart any piece of request, if I can impart a request from you, please, just tonight, or maybe like at 3 hours after class, just do a little bit of practice, please, for me. Pour one out for your homies, as you kids say, or whatever, and then take a shot for me, a shot of Mountain Dew, I'm assuming. And then do 2 problems. Just two, please. I'm just begging you, just do 2 of them. Okay. And you can do 2 and then have a nice nappy nap. Okay, please. This next one, the integral of y cubed times the square root of y to the 4th plus 2 dy. What would be a good choice for you? Take a second. Based on our little typical choices, the correct choice would be the inside of that radical. So we're going to make u equal to y to the 4th plus 2. That would mean that du dy would be 4y cubed, but we're gonna secretly multiply by dy. We're gonna get du is equal to 4y cubed dy. At which point we will solve for dy. We're gonna divide both sides by 4y cubed. I'm gonna stop writing this after a certain point, because I can trust you to do this algebra in your head. But if you but I'm going to keep writing it for now. So you get dy is equal to 1 over 4y cubed du. And so this is equal to then the integral of y cubed. Nothing happened to the y cubed yet, because that's not what we claimed u to be. Get y cubed? Nope. Interesting. So, any questions so far in this process? And please feel free to ask. Like this is probably one of the more complicated concepts of Math 181, in my opinion. It's definitely strange when you first experience it. Just like the chain rule. Remember, the chain rule was really weird when we first started, but as we got more and more practice, it became kind of second nature. Same idea here. So now that we've got that, the square root of y to the 4th plus 2 is now the square root of u. And then dy is now 1 over 4y cubed du. And lucky for us, the y cubeds cancel. And since we're going to be needing to integrate this, I'm always going to convert, just like with differentiation, right? Whenever we saw a radical, we always converted it to exponential form because that made it easier to do the power rule. So we're going to do that here. So we're going to write this then as the integral of 1/4 u to the 1/2 du. And that's an integral purely in terms of u. So we can integrate it and have a great time and a grand old time. That'll be 1/4 u to the 3 halves over 3 halves plus a constant c. But dividing by a fraction is the same thing as flipping and multiplying. So this is really 1/4 times 2/3 u to the 3/2 plus c. And at the end of the day, that would be 1/6 times u, which is y to the 4th plus 2 to the 3/2 power plus a constant c. Any questions on that one? Yeah, the thing I love about integrals especially is the fact that we can always check our work. So you can actually literally just practice, and this is twofold. This is a win-win-win, is that you're practicing your integration, and if you want to check your work, you're practicing your differentiation skills. Because if you check the dy of 1/6 times y to the 4th plus 2 to the 3/2 plus a constant c, that would be 1/6, the constant, times 3/2 times y to the 4th plus 2 to the 1/2, because you're doing the chain rule, the outer function being the 3/2 power. So 3/2 comes down, reduce the power by 1, and then you multiply by the derivative of the inside, which is 4y cubed, and then plus 0 because the derivative of constant is 0. And if you do this, you should get y cubed times y to the 4th plus 2 to the 1/2 power, or y cubed square root of y to the 4th plus 2. Exactly what we started with. So you know you can do it, you can check your work. That's the beauty of indefinite integrals, is that you can check your answers. Most of the time. There are a few circumstances where checking your work becomes a very, very tedious task. But for the most part, if it's a nice, simple u substitution like this one, simple not meaning easy, but simple meaning like a non-complicated formula, like a reverse engineered u substitution, it 9 times out of 10 will prove to be the same number. So pretty cool. And the other thing that I just want to comment on that's really cool about integration is that if I were to change that just slightly, instead of being y cubed square root of y to the 4th or whatever, if I added an assigned y like this, don't write this down, this is just for observation. If I were to try and find the integral of this, I couldn't. There is no formula that I can find that will break this down into something and I can write a formula. There's no way to do it, which is crazy. We know that it does exist because that is a continuous function. That function exists everywhere, but there is no way to actually find what it equals, which is a very humbling thing about mathematics. It happens a lot as you continue onwards. Like we'll talk about this function right here, 5n over 33n to the 3rd power plus 2. And we'll talk about this going from n equals 1 to infinity. And we'll ask ourselves, does this thing converge? And the answer is it will, but we have no idea what it converges to. We have no idea what that number is, but we do know that it converges, which is a very, very, like, you have to become, as a mathematician, you have to become okay with that fact that there are things that you know that are true, but you don't know more about them. There's a very, I think I talked about it in this class. Did I talk about Gödel? This guy? Did I talk about him? He, famous mathematician, he studied mathematical logic, which I think I've talked about here, is the most meta of meta fields at all. It's proving that proofs work. It's proving that the proof is an actual proof of something. So it's very meta. It's a ridiculous field, but Gödel, he figured out a theorem that said, the incompleteness theorem, that says that in any proof structure that we can create, typically mathematics, there will be things that are true that cannot be proven. And so this, like what I just wrote prior to that, is a prime example of something that we know exists. We know what this equals. Like we know that this has an integral, but we don't know what it is, which is just bonkers to me. We've always assumed in mathematics that there's always an answer, and there is, but sometimes we just can't find it. So anyways, I'm getting sidetracked. Next one. The integral of 6x squared plus 8x minus 10 over x cubed plus 2x squared minus 5x plus 6. What do you think a good choice for you would be? Take a second. Based on my recommendations, the choice would be the denominator. Let's make u equal to x cubed plus 2x squared minus 5x plus 6. Right now, by the way, you guys are building up what I would like to consider your integration tool belt. This tool belt will get more expansive. It won't just be like a hammer in your back pocket when you're climbing up a ladder. It'll be one of those badass toolkits that you see people wear, every dad wear, right? Has all the tools on it. You'll eventually get to that point in Math 182, but for right now, you've got like basically a screwdriver, a hammer, and a pair of pliers, and you're trying to learn what tool to use in what situation. Sometimes and the more you work, the more you work in construction, the better you get at realizing what is a useful tool and what is not a useful tool in any circumstance. Same thing is going to be here. You're going to realize that trying to do a u substitution of just x cubed or something like that is not going to work. And the more integrals you encounter, the more problems you've experienced, and the better you will be at it. So anyways, du here then would be 3x squared plus 4x minus 5. And remember, this whole thing has to be multiplied by dx. Every single time, the whole derivative is multiplied by dx, not just the last term. So please write your parentheses every time. When it comes to u substitution, please write your parentheses every time. Because remember, what's happening in the background, at the end of the day, you've got this little tiny implied step that you write du dx is equal to 3x squared plus 2 or plus 4x minus 5, and then you're going to multiply both sides by dx. That's why you always want to put it in parentheses, because you're multiplying the entire right side by that dx. In quotation marks. So please don't forget that. It breaks my heart. I've seen it happen so many times where students will write this instead. So don't write this down. This is not correct. But I'll see students write down du is equal to 3x squared plus 4x minus 5 dx. And then they'll try and solve for dx there. And that will get you into a world of hurt. That's way too, that's hyperbole right there. You're not going to be hurt because of that. Like mentally anguished maybe, but not actually like physically hit. Unless I'm there and I can bop you on the head like a bad dog, bad student. So now we solve for dx. We get dx is equal to 1 over 3x squared plus 4x minus 5 du. And so this then becomes the integral of 6x squared plus 8x minus 10, all divided by u, that's what we claimed u to be, times 1 over 3x squared plus 4x minus 5 du. And then the haters are going to come at me and say, Phil, that doesn't work out. That doesn't cancel. Yes, it does. There's a common factor. The 6x squared plus 8x minus 10, if you were to factor out a common factor of 2, so right here, this is 2 times 3x squared plus 4x minus 5. And there we go. Now we can cancel those. So sometimes you need to do a little extra algebra after you make your u substitution. If you do that, then this integral, the integral of 2 over u du, and you just saw this on the quiz. What's the antiderivative of that? Natural log. 2 natural log of the absolute value of u plus a constant c, which then at the final stage would be 2 ln absolute value of x cubed plus 2x squared minus 5x plus 6 plus a constant c. When it comes to these problems, by the way, feel free to skip as much algebra as you want. So, like, I'm going to talk about that once you guys have written it down. Explain what I mean. That one, and then what? All right. So, if you want to go straight from here to here, you be my guest. If you don't want to write the u state, like the actual integral with respect to u, and just go straight to the answer, that is fine with me. That saves on time. But I usually like to do that, especially if I have to do some algebra along the way, if I have to do some arithmetic like we did in this problem here. Just so I don't have to like when I'm doing my arithmetic, I don't have to rewrite something nasty. So that's what I typically wait until I've simplified it so that I only have to write one u instead of writing like y to the fourth plus 2. Because like that made me save. So 1 pen stroke versus 1, 2, 3, 4, 5, 6. 6 pen strokes saved. Sorry, 5 pen strokes technically. That adds up. Anyways, any questions on that one? All right, we'll do one more and then we'll take a break. Sine squared theta times cosine of theta. So there's no really large powers, but there is one that actually has a power. The sine does. So that would be the go-to. But what happens if you don't know what to choose and you maybe choose, well, maybe I make u equal to sine squared theta. Well, then du would equal to, this is not correct, by the way, so this is not going to work out, but 2 sine theta cosine theta d theta, which means that d theta is equal to 1 over 2 sine theta cosine theta du, and this would then become the integral of u times cosine of theta times 1 over 2 sine theta cosine theta du. And so a little bit cancels, the cosines cancel, but that sine doesn't cancel really well. There is something you can do here, by the way, to actually solve it, but it requires a lot of being very clever. So what you would do is instead change this back to a sine squared theta for a second, cancel one of the factors, and then realize that u is equal to the square, like sine squared theta is equal to u, so that means that that's integral substitute. That's reverse engineered u substitution. But point being is, you'll notice when you try and do a wrong u substitution, things won't cancel nicely. So instead, we'll make u equal to sine of theta. Because remember, this is the same thing as sine of theta quantity squared. So we're going to make u equal to the inside of that power, sine of theta. That would mean that du is equal to cosine theta d theta. It's like the best theta I've ever drawn. It's beautiful. I used to draw my thetas like this, that thing, trying to do it in one pen stroke. But I just realized that was just unnecessary. So d theta is equal to 1 over cosine of theta du. So this becomes the integral of u squared now, because u is equal to sine theta. So u squared times cosine of theta times 1 over cosine of theta du. And the cosine thetas cancel. And we're going to have the integral purely in terms of u. We're going to have an integral of u squared du. I did this one deliberately to try and relate to the kids because it says, dude. Sup, dude. No. Didn't actually. It's a dumb joke. I'm not going to do that ever again. Okay, good enough. This becomes 1/3 u to the third power plus a constant c. At the end of the day, that would be 1/3 times sine cubed of theta plus a constant c. Any questions on that? It's okay if there are. It's again there. It's okay if there are. Okay, we're gonna take a break. We're gonna take about a 5-minute break. We'll come back at 10:13. So people watching the recording, go ahead and take a little break, get a snack. We're back. So we get to do this one. The integral of u plus 1 times e to the u squared plus 2u du. So good choice for an integral substitution would be, in this case, you could try to do u plus 1, but that really wouldn't get us much. You could try it if you want to, but it won't get anywhere. And then the only thing left then would be the exponent of the u. So we make u equal to, oh, wait a minute. The variable in question is u. What are we to do? Change to a different variable. It doesn't matter what you do. Just choose what's right for you. I know I love that, making that joke. I'm sorry, I just can't stop. You could do v. That's usually a good choice. W is a good choice. A, B, C, whatever you really want to. My only recommendation is if you do use v, I really recommend to make sure it is very, very crisp, that point. I only mention this because if you decide to take 182, you will talk about integration by parts, which is this integral of u dv, which ends up being uv minus the integral of v du. Don't worry about that. You'll get that later. It's not important. But the point being is if you lazily write your v's, it's not really clear which one's which. And so you're gonna cause yourself a lot of anguish if you don't make sure. So from this point on in your mathematical career, always make your u's have tails. Your u's should always look like this, regardless of if it's a capital or a lowercase. Always do a tail. And then for your v's, just make sure it's a very, very specific point. The easy way to bypass that, though, and this is what I have done because I don't trust myself, is I just make my v's very, very large. So v is equal to u squared plus 2u, but you can use t, you could use x, you could use b, it doesn't matter. I'm going to use capital V essentially to really distinguish it from a lowercase, from a u. And that would mean that dv is equal to 2u plus 2 quantity multiplied by du. And then solve for du, you get du is equal to 1 over 2u plus 2 dv. So this equals the integral of u plus 1. That hasn't changed. But then it's e to the v times 1 over 2u plus 2 dv. And it doesn't look like it cancels or does anything yet, but that's not true. There is a nice factor of 2 that can be brought out front. And then the u plus 1s cancel. So we have the integral of 1/2, because that 2 is sticking around in the denominator, e to the v dv. And the integral of e to the v is itself. So this will be 1/2 e to the v plus a constant c, but v was claimed to be u squared plus 2u. So at the end of the day, we have 1/2 e to the u squared plus 2u plus a constant c. Any questions on that? Yes, Chief.
We can, probably with the key and greater than what happened.
No, that'd be fine. Like writing as e, like instead of, so she's asking, could we write it as e to the u squared plus 2u over 2? That is totally fine. Yeah. Any teacher who doesn't, let me know. We'll get into it. We'll get into a battle. B, my is a very, very favorite one. So you could try to make it just, this is what the the recommendation number 2 is mentioning with sometimes in conjunction with with option 1. So you could try to do it, and I'm gonna do it deliberately here to say, let's make it the whole denominator. So don't write this down, but like if u equals t times ln of t squared, then du by the chain rule, or product rule in the chain rule, this is f, this is g, so it'd be f prime 1 ln of t quantity squared plus 2 ln of t to the first power times 1 over t times t, and then all times dt. Now, this doesn't necessarily mean that it's on the wrong path yet. We're not certain. We're still doing it correctly, but we're not certain if this is going to get anywhere. But this ends up being ln of t quantity squared plus 2 ln of t dt. And you'll notice that this isn't going to really get us anywhere. There's no way, there's no pluses in that thing in the original integrand. On the inside of the integral, there's no pluses. So there's probably not going to be any way for us to cancel here. That means that this isn't the right choice. So we've got to go back to the drawing board, erase this, and try something new. So you could try and make it ln of t quantity squared, but that also will not end up coming to fruition. So the best choice would be to make u equal to ln of t. Then du would be 1 over t dt. And so instead of dividing this time, now we got to multiply. So we can still do all of that stuff. We don't have to always, it's not always division to solve for dt. Here, I'm going to multiply both sides by t to cancel it on the left and get that dt is t du. And if I do that, I get that this equals the integral of 1 over t times u squared times t du. And the t's will cancel. And we've got the integral of 1 over u squared, which looks like it's not going to work out, but then we got to remember to use our properties of exponents. So it's 1 over u squared du, but that's the same thing as the integral of u to the negative 2 du. And that I can integrate with the power rule. Add the powers and call it good. This equals u to the negative 1 over negative 1 plus a constant c. And at the end of the day, that would be negative quantity ln of t to the negative 1 plus a constant c. You can rewrite it in a prettier format if you really want to, but it's unnecessary because we're not using it for anything. But any questions on that? All right. So on this next one, I'm going to do it the wrong way. I'll keep this up here in case people are still writing. I'm going to do it not the wrong way. So what she was asking earlier in the hour was asking about whether or not there's like multiple ways to do things. And there are. And this is one of the things that can happen is sometimes you'll make a u substitution and you won't get you won't be able to integrate, but you'll get closer. And so if that happens, you can sometimes do an additional integral substitution to try to figure it out. So I'm going to show you that process. That's not the fastest way. Anytime that you can do 2 integral substitutions, it can be solved in 1. And I'll show you that in just a moment. So don't write this down because this is not the proper way. But it will practice it twice. So it's good practice to watch because it does end up working out. This isn't like the previous times where it didn't work out. So we're looking at this problem and we have 2 of our common options. There is something inside of a large power and there is a denominator. So let's just say for the sake of an argument, you decided to do u equal to the denominator. So this is not going to be the best way. So I'm going to make u equal to the square root of x, which is x to the 1/2, so that du would equal 1/2 x to the 1/2, negative 1/2, excuse me, dx. And remember, since I'm utilizing this to solve for dx, I'm going to simplify it first. Since I'm going to be needing to use this to solve for dx, I'm going to rewrite it. This is 1 over 2 square root x dx. So to solve for dx here, I would multiply both sides by 2 square root x and get the dx is equal to 2 square root x du. So if I do that, then this would become the integral of 5u, remember, because square root x is u. So 5u plus 1 to the 10th power divided by u times 2 square root x du. And that looks like nothing's going to happen, but remember what u is. U is the square root of x. So the u's do cancel. And what we end up with is the integral of 2 times 5u plus 10, plus 1 to the 10th power du. And now that's simpler, but I still can't do anything with it yet because there's no way to deal with the 10th power without doing another integral substitution. You could, if you really wanted to, if this is you on the exam, you could FOIL that out. You absolutely could and get the right answer. Not recommended, but you could. But the option then would be to do a second integral substitution. So we've already used the variable u, so let's just use, I don't know, let's use w. Let's make w equal to 5u plus 1, the inside of the large power, right? Then dw is equal to 5 du. So that means that du is equal to 1/5 dw. And so this will equal then, now that we solve for du in terms of dw, not Arthur's little sister, you know what I'm talking about, is equal to the integral of w to the 10th over, we're not there, here, 2w to the 10th times 1/5 dw. And that we can compute. That's going to be 2/5 times w to the 11th over 11 plus a constant c. What's going on here is that the 2 and the 1/5 are out front. The integral of w to the 10th would be w to the 10 plus 1 over 10 plus 1, or w to the 11th over 11 plus constant c. And now we've integrated, so we can start working backwards. W was claimed to be 5u plus 1, so this is 2/55 times 5u plus 1 to the 11th power plus a constant c, but u was claimed to be square root x. So at the very end of the day, we have this 2/55 times 5 square root x plus 1 to the 11th power plus a constant c. So, and that would give you the right answer. You had to do 2 u substitutions. I like to call this a w substitution. That's the joke, guys. That's the joke. Get it? Get it? It's a w and it was a 2u substitution. Boom. I told that joke to Dr. Bill at OSU. He's never smiled once in his life. Fairly certain he came out babies usually smile within the first 6 months of life. Didn't smile at all. But I told that joke during a grading party and he smiled. So that's why I know this is the funniest joke that has ever existed in humankind. You are welcome. There you go. Thank you. I will be here for 2 more weeks. But anyways, that is the joke. I came up with that myself, and I'm very proud of myself. And fun fact about this, I need to turn this on. People watching the recording, you won't be able to get to see this. When I write notes for my classes, I typically write in color just like I normally do. So like you can see color on these pages. If I write anything in my notes in orange, it's something that I say but don't write down. So it's like either an important anecdote about the history of something or something like that, something that I usually want to do. So, true story. Let's see if this, oh, you can't even read that. Let's auto-tune. So that's what I wrote. That's in orange, you can't tell. So do the joke, everyone laughs. I feel good about myself for the first time in a long time. I have that on my notes because that is how I get through the semester. That's what I look forward to every semester when I teach 182. It's the only reason why I teach anymore. Exactly. It's the only reason why I teach, guys, just to make that joke. Now I can quit. Anyways, man, I forgot to chart. That doesn't matter. Okay. So the proper way the faster way. So I'm gonna put it back up here for just one moment. We did a u substitution of square root x, and then we did a u substitution of 5u plus 1. Anytime you can do two u substitutions, they can be done in one. So what we can do is instead, we make the correct choice would be to choose the numerator, the inside of the power. U equals 5 square root x plus 1, which is 5x to the 1/2 plus 1. So du would therefore be 5/2 times x to the negative 1/2 dx. And since I'm going to be solving for dx, I'm going to simplify this. I'm going to rewrite it in radical form to make it easier to approach. So du will equal 5 over 2 square root x dx. And in order to solve for dx, you can either divide by 5 over 2 square root x and flip and multiply, but I'd rather just get some practice doing some more algebra. I'm going to multiply by the reciprocal. So I'm going to multiply by 2 square root x over 5 to cancel it on the right-hand side. And get that dx is equal to 2 square root x over 5 du. This becomes a lot faster now. You'll see, like we're almost done. Instead of having to do that whole thing, that was literally just the setup for the joke, though, honestly. Way too fun. Where were we? So we're going to replace it. So this is equal to the integral. U was claimed to be the entire inside of the numerator. So that would be u to the 10th divided by the square root of x times 2 square root x all over 5 du. And now the x's cancel. And that's going to be the integral of 2/5 u to the 10th du. So at the end of the day, that's 2 over 5 times u to the 11th over 11 plus a constant c. And that becomes 2 over 55 times 5 square root x plus 1 to the 11th power plus a constant c. At the end of the day, we get the exact same answer, regardless of whether we do the w substitution or not. Like, I know you guys are going to be thinking about it later. I know you guys will be, and just you'll be thinking about that later, and that's what I have to tell myself to make sure that I can survive another day. So, anywho, any questions on the actual way to do this problem? Not the actual way; both ways work. But next one, this one is to show us that sometimes we have to break things up. An option to do, so when you see this one, you might want to try to do a myriad of things. But the problem is that there's no real consensus. Now, I would 100%, if this problem popped up on the final exam, once again, I don't know because I haven't gotten it yet. I'm probably going to get it next week in preparation for the final exam. So I'll probably get it next week. But if this one were to pop up, one option that you might think about doing would be to find a common denominator. That would be a good option. It won't work out, but if a student did that on an exam and got stumped, I'd still give some partial credit for that because that's a good idea to start. It doesn't work out, and so what we do instead is we actually have to split it up. If we split it up into pieces, the integral of x times the square root of x squared plus 1 dx plus the integral of 1 over the square root of 1 minus x squared dx. Then you'll notice the second integral is something we actually already know. The second integral is inverse sine. The second integral is inverse sine. The first integral will require a u substitution. So sometimes you'll have to do two u substitutions at the same time. Sometimes you will have to do a myriad of things. It doesn't matter. The key thing is to just keep trying. Just imagine imagine you're trying to make a cool Lego spaceship, and you're trying to figure out what you want to do next. Maybe you try and add some cool badass wings on the sides, but ends up being that you don't have two of the black wings. You only have two left wings. If you know what I'm talking about, it's the worst feeling in the world when you're trying to play with Legos. If you have two of, like, you guys remember the wing, this wing, but then you're like, oh, I have two of them, but then you realize that the other one is just like you have this one, and you think that you have two of them, but it ends up being that they're the exact same thing, so it can't work out. It's the worst feeling in the world. But anyways, this one, if this ends up happening, I usually like to break this up into steps. I like to do them in pieces and come together, especially if they both require U substitutions. I don't want to try and do two U substitutions at the exact same time. That's just a mess. That's a recipe for making an error, a mental error somewhere. So what I'm going to do is for this one, for integral of x, square root of x squared plus 1 dx, I'm going to do the U substitution. What do you guys think U should be? X squared plus 1. That's the right choice. Don't worry if you're not there yet. This takes time. This takes time to find out what the right choice is. So then du will equal 2x dx, which means that dx, if you solve for it, would be 1 over 2x du. This is the way I'm typically going to write it from now on. I'm still going to write it for this one just one more time to show you that I'm solving for dx, but I encourage you to get to the point where you don't need to write this extra step and save yourself a little bit of scribblings. But I do that, and then I get dx is equal to 1 over 2x du. So this becomes the integral of x times u to the 1/2. I'm going to convert it to exponential form right off the bat because I know that it's we're looking concerned. Okay. I know that I'm going to have to integrate that thing anyways, so I'm going to convert it to exponential form. Not wrong to write it as square root u and then convert it. It's just an extra saving us time. Times 1 over 2x du. The x's cancel. And we end up with the integral of 1 over 2 u to the 1/2 du. And we can compute that pretty nicely. That will be 1/2 u to the 3/2 over 3/2 plus a constant c, which would be, if you flip and multiply, you're going to be 1/2. I can write it out. That'll be 1/2 times 2/3 u to the 3/2 plus a constant c. And so that gives us 1/3 times x squared plus 1 to the 3/2. And actually, you know what? I'm not even going to write the plus c. I'm not even going to write the plus c, because I just want to write the plus c at the very, very end. You can add two constants, right? You could do sine inverse of x plus a constant c and this one plus a constant d. And that's not wrong to do, but we can combine them into a global constant at the very, very end. So the final answer will be that this is 1/3 x squared plus 1 to the 3/2 plus sine inverse of x plus a big constant c. Though if you write it as two constants, you will get full credit. No problems there. It's not wrong to write it as two constants. It's just it makes it end up being a little more work in the long run. Cool? Hey, oh, gee, yes.
You don't have like way, I can cannot like the like half. You use up for the second half or
So if you don't remember your inverse trig integrals, this one will actually be unsolvable for us. 182, you will find a way to do it called trigonometric substitution, but at this point we don't have that. If you want to know about trigonometric substitution ahead of time, absolutely talk to me. It's a great technique. But the yeah, that one would be like, you would like, if that's the case on this exam, break it up and let me know. Do this one over here. Say, I don't remember what this is. I think this is a special integral, but I don't remember. I will give you a point back. If you know that it's supposed to be something, but you don't know it, and you get this all correct, I will give you some extra partial credit there. So it's a big thing to learn in mathematics, is to be humble about not knowing everything. We do. Yes.
we were to learn it trigonometric substitution before the x was up, you did.
Yes, you would, absolutely. Because trigonometric substitution is just U substitution with a very, very clever idea in mind. It's a lot more complicated than regular U substitution. If we have time, like we got to do these. We need to do this last one, and I was going to let students do that one. So the way it works is you make sine of theta. In this case, you'd make sine of theta equal to x, so that cosine of theta is equal to 1. Wait, it's been a while. It's been a while. If that's the case, then
Say you can't prevent it.
No, like
Not gonna use it in this part.
no, like the thing is, I know exactly like how I would do it, but that's me making it up on the spot, and I don't want to confuse you with what you're going to see in 182. There is a very, very systematic way, but I don't want to bog you down with the crazy ideas that I'm going to put out on there. But so I say, if you do learn trigonometric substitution, since it is just a form of integral substitution, you get full credit. But this last one. Find the indefinite integral natural log of tangent of theta over sine theta cosine theta. I added this one this year because I love this problem. This is really trying to show you that you really just have to get your hands dirty. So there's a lot of options here. So we could try and do the denominator. And let's just see where that goes for just a moment. So this is not correct. This will not work out. But let's make u equal to sine theta cosine theta. Make it equal to the denominator. If you do that, then du by the product rule would be cosine theta, depth cosine theta, plus negative sine theta times sine theta, and then all times d theta. And so you get du. Already, you should probably be looking at this and saying, well, this probably isn't going to work. There's no addition or subtraction in here. But if you were clever enough, you'd have cosine squared of theta minus sine squared of theta. And who remembers this? Who remembers that trig formula? Remembers it? Come on. Anybody? Anybody? Does anybody remember what cosine squared minus sine squared is equal to? Cosine squared plus sine squared is 1. This one is, I think it's 2, it's sine of 2 theta, I believe. I think so. I think it's sine of 2 theta. It might be sine of 2 theta over 2. I think it's like this. And that would be cool. And I'd give you 100, like I give you kudos, right? Kudos for knowing your trig. But unfortunately, there's no sine 2 thetas here that can help us out. So that doesn't work out. So that isn't going to work. And that's okay. We tried and we failed, but that means we just get back up again. So a better option, we could try natural log of tangent of theta. We can try the inside. Let's try u equals tangent of theta. This also isn't going to work. But let's try it. If u is equal to tangent of theta, then du is equal to secant squared theta, d theta. And I don't see any secant squares, but I do know that secant is 1 over cosine. So I could write this as 1 over cosine squared theta, d theta, so that d theta is equal to cosine squared theta du. And so let's see what happens. This becomes the integral of natural log of u divided by sine theta cosine theta times cosine squared theta du. And we get a little bit of cancelization, but we don't get all of it. We'll have an ln of u over a sine theta du, and it doesn't work out. Another option that a student suggested last class, in my other class, which I thought was very clever, was to convert it to sine over cosine and do natural log of sine theta minus natural log of cosine theta by using the properties of logarithms. Also, great idea. I don't think it works out, but still a cool idea, and you get partial credit absolutely for being clever. But neither of those worked. So u equals the denominator didn't work. U equals the inside of the logarithm didn't work. So what are we to do? What do we do? Cry? Just give up. Say, I can't do this, and leave the exam and get everyone to be creeped out. That sounds like a good idea. I like it. I like it. Better option, we haven't tried, like, what haven't we tried? We've tried the inside of the logarithm. We tried the denominator. There's one thing we haven't tried. Why not try the whole numerator? Why not try it? What's the worst thing that can happen? We erase it. So we'll make u equal to natural log of tangent of theta. So I hope the reason why I chose to do u equals sine theta cosine theta is to remind us of something, which I'll get to in a second. That would mean by the chain rule, du is equal to 1 over tangent of theta times the derivative of tangent theta, which would be secant squared theta, d theta. The reason why I brought up using u equals sine theta cosine theta is to remind us that, so right now it doesn't look like it's going to work out. It will, and there's the thing we need to do is work with the trig. Work with it. Know the tangent, well, whenever you're dealing with trigonometry, always a good option if you're stumped to convert it into sines and cosines. Always a good option. And so let's simplify it a little bit before we solve for it. Remember that tangent is sine theta over cosine theta. And you're dividing by it, so that's really cosine theta over sine theta. So this means that du is equal to cosine theta over sine theta times 1 over cosine squared theta d theta. And one of the cosines cancels here just by simplification, because remember, we're solving for d theta. If we're gonna use something, we want to simplify it first. So we'll cancel one of those factors. We get that du is equal to 1 over sine theta cosine theta d theta. And so what we would do is we'd multiply both sides by sine theta cosine theta. Cancel it on the right and get our get d theta is equal to sine of theta cosine of theta du. I'm going to take a step back. Let's recap because that's a lot of work. We still got enough time. I'm going to write down while you guys are writing it down. I'm going to write the answer to this next one so that you can check this one at home over the weekend, hanging out with your mom and pop, or your girlfriend, boyfriend, significant other, whatever it may be, or your buddies. It'd be a good problem to do. So cosine out. Keep writing. Sine of ln of z plus 1/5 e to the z plus a constant c. We're gonna finish up this last problem that we're doing, and then we're gonna call it good. But if you want to check your work, please just do this problem, please, tonight. 5 minutes after class. I don't care. Just do a little bit of practice so that it stays in your head. So anyways, back to our problem at hand. Don't worry, I'm going to scroll back down to that if you haven't written it yet. But make u equal to natural log of tangent. So by the chain rule, derivative of the outside, 1 over tangent theta times the derivative of the inside, secant squared. And then whenever you're dealing with trig, if it doesn't end up being nice and neat and working out, always try and break it down into nicer pieces, sines and cosines, or try and use trig identities like sine squared plus cosine squared is equal to 1, or 1 is equal to secant squared plus 1, or 1 minus secant squared, I think. Whatever it may be, I don't remember off the top of my head. I'd have to deduce it. But anyways, we convert it. Tangent of theta is sine over cosine, but it's 1 over tangent, so that's why it's now cosine over sine. Secant squared is 1 over cosine squared. One of the cosines cancels. So we've got du is equal to 1 over sine theta cosine theta d theta. We want to solve for d theta. That's the last step, or the second to last step. Multiply both sides by sine theta cosine theta, and you get d theta is equal to sine theta cosine theta du. So this becomes the integral of u over sine theta cosine theta times sine theta cosine theta du. And boom, those both cancel. And we've just got a nice integral of u du. And so that'll be u to the second power over 2 plus c And at the end of the day, that would be natural log of tangent of theta squared over 2 plus a constant c. So now we've seen a situation that didn't fall into one of our categories. Is that like, and now we know more. We punched a hole in our wall on accident, on purpose. And we're trying to fix the drywall. So we try and take a hammer to it and it doesn't work out. But it did make us learn something. We made a better square so we could put a new piece of drywall in, cover that up, and then use like the whole, whatever that trick is where you like put a piece of 2x4 and you drill it in, whatever it may be. I'm not very good at that, but that's the idea. You learn from your mistakes. You accidentally made the hole bigger, but that actually made you learn how to properly get it covered up. So anyways, that'll be it for that one. Is there any questions on that? Please just practice tonight. I'm begging you. I'm begging you. If you want to take 182, you need to know this. So anyways, that'll be it for today. If you have any questions, feel free to ask. Otherwise, you guys have a great rest of your day, a great weekend, and I'll see you guys on Tuesday.